Nothing in the universe truly disappears. Even the most violent events we know, collapsing stars, torn spacetime, swallowed light, must still obey the quiet rules of physics. Energy is conserved, information leaves traces, and somewhere, hidden in equations more than in observation, there may exist objects that do not consume the universe, but return it. If this quiet exploration brings you even a moment of calm or wonder, I'm deeply grateful you're here. A gentle like, a soft tap on subscribe, or simply your presence helps keep this small corner of curiosity alive, and it truly means more than you know. Now, with that stillness settled around us, we begin. Part 1. What is a white hole? Really, a white hole is not something we've ever seen through a telescope. It appears first in mathematics, emerging naturally from the same equations that predict black holes. When physicists solve Einstein's equations of general relativity, they find that spacetime allows not only regions where matter and light fall inward forever, but also the theoretical reverse, regions where matter can only move outward, never in. A white hole, in this sense, is not a fantasy, but a lawful possibility written into gravity itself. To understand why white holes exist at all, we have to slow down and look carefully at what Einstein's equations are actually doing. General relativity does not describe objects in the traditional sense. It describes relationships between mass, energy, space, and time. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. When those equations are pushed to their limits, when gravity becomes extreme, they reveal behaviors that feel deeply unfamiliar to human intuition. Black holes are one such behavior. They form when mass collapses into a region so dense that spacetime curves inward without escape. Past the event horizon, every possible path points toward the center. Light cannot climb out. Time itself tilts inward, but the equations do not stop there. When physicists explore the full mathematical structure of these solutions, they find that the equations are symmetrical in time. If inward collapse is allowed, then outward emergence is also allowed. The mirror image appears automatically. This mirror image is what we call a white hole. In the simplest terms, a white hole is a region of spacetime that cannot be entered from the outside. Just as nothing can escape a black hole, nothing can fall into a white hole. Matter, radiation, and light are permitted only one direction of travel, outward. From the perspective of physics, this is not an added assumption. It is simply what the equations permit when time symmetry is respected. This idea first emerged in the early 20th century, not as speculation, but as a mathematical consequence. Carl Schwarzschild, the physicist who discovered the first exact solution to Einstein's equations in 1916, found that his equations described more than one kind of horizon. Decades later, when physicists fully mapped the structure of these solutions, they realized that black holes and white holes appear together in the same mathematical spacetime. In these extended solutions, spacetime is not a single collapsing region, but a larger geometric structure. A black hole represents a future boundary, something you fall into. A white hole represents a past boundary, something you emerge from. In this view, white holes are not objects that form over time. They simply exist as part of spacetime's structure, already complete. This is where the idea begins to feel unsettling. A black hole forms through a process we understand. A star collapses, gravity overwhelms pressure, and an event horizon appears. But a white hole does not form this way. There is no known physical mechanism that causes a white hole to come into being through collapse. Instead, it exists fully formed, expelling matter as if from nowhere. From the outside, a white hole would look like a sudden eruption. Matter appears, streams outward, and cannot be traced back to any internal cause. There is no star inside, no fuel, no visible engine, just emergence. This violates our everyday understanding of causality. We are used to thinking that things happen because of something that happened before. But a white hole behaves as though its defining event lies in the past beyond reach, not in the future. In technical terms, it is a solution that is time-reversed relative to black holes. Time reversal is not science fiction. Many fundamental laws of physics work equally well forward and backward in time. The equations that describe gravity do not care which direction time flows. They simply describe relationships. The arrow of time we experience, the sense that causes come before effects, is not built into gravity itself. It emerges from thermodynamics, from entropy, from the collective behavior of many particles. White holes exist comfortably within time-symmetric equations, but they clash with the thermodynamic arrow of time that dominates our universe. This tension is one of the reasons white holes remain theoretical. They are allowed by gravity, but discouraged by the universe's tendency toward increasing disorder. A white hole represents a decrease in entropy. Matter emerges in an organized way. Energy flows outward from a confined region without dispersing first. This makes white holes deeply unstable in realistic conditions. Even so, their mathematical existence is important. White holes teach us that black holes are not the end of a story, but part of a larger structure. They suggest that spacetime, under extreme conditions, may include boundaries that act not only as sinks, but as sources. And they force physicists to confront uncomfortable questions about beginnings and endings. If a white hole exists, where did its matter come from? The equations themselves do not answer this. They simply state that matter emerges. Some interpretations suggest that white holes are connected to black holes through deeper structures, such as wormholes or extended spacetime geometries. In these speculative models, what falls into a black hole does not vanish. Instead, it may reemerge elsewhere, perhaps in another region of spacetime or even another universe, as a white hole. Other interpretations avoid such connections entirely and treat white holes as isolated features, cosmic boundaries where spacetime itself begins. In this view, a white hole is less like an object and more like an origin event, a place where the equations stop asking what came before. This idea has an echo that feels familiar. The Big Bang itself shares some striking similarities with a white hole. Everything emerged, nothing entered. Space expanded outward from a boundary that does not exist within time as we understand it. While physicists are careful not to equate the Big Bang with a white hole directly, the resemblance is not accidental. Both arise from the same gravitational mathematics pushed to their limits. Importantly, none of this requires belief in exotic or mystical forces. White holes are not supernatural. They do not violate physics. They obey Einstein's equations exactly. Their strangeness comes not from breaking rules, but from following them too completely. If you imagine standing far away from a hypothetical white hole, you would not see a glowing sphere labeled with meaning. You would see matter streaming outward, redshifted, as it escapes a strong gravitational field. Time near the horizon would behave strangely. Signals from the emerging matter would appear distorted, stretched, and delayed. But there would be no way to approach the source itself. Every attempt to move inward would fail, not because of a force pushing you away, but because spacetime would not permit the path. In that sense, white holes are defined more by what they forbid than what they allow. They forbid entry. They forbid inspection. They forbid causal explanation from within our timeline. And yet, they remain quiet possibilities, resting patiently inside equations written over a century ago. Whether white holes exist in our universe is still unknown. No observation has confirmed them. No experiment has isolated their signature. But their presence in our theories matters. They remind us that gravity is deeper than collapse, that spacetime may have exits as well as entrances, and that the universe may be capable of behaviors that feel profoundly one-sided to our experience. As we continue this quiet journey, one question naturally rises next. If white holes are allowed by the laws of physics, why does the universe seem so reluctant to create them at all? Part 2. The mirror image of a black hole. If a black hole is defined by what it does, pulling everything inward beyond a point of no return, then a white hole is defined by refusal. Nothing can enter it. Matter, energy, even light are permitted only one direction, outward. From the outside, this makes a white hole appear less like an object and more like an event, a boundary where the universe releases something it will never take back. It is gravity turned inside out, at least in principle. To understand this mirror relationship, it helps to begin with the quiet geometry of spacetime itself. In general relativity, gravity is not a force pulling on objects. It is the curvature of space and time, guiding motion along invisible paths called geodesics. Every particle, every beam of light, simply follows the straightest possible route through a curved universe. A black hole forms when those routes all tilt inward. No matter where you try to go, space-time leads you deeper. A white hole reverses that tilt. Instead of paths converging inward, every allowed path points outward. The geometry does not permit approach. Even light, which normally traces the most direct routes available, finds no inward trajectory. From the moment something emerges, space-time carries it away, stretching distance between it and the horizon behind it. This reversal is not a matter of swapping labels or imagining anti-gravity. The equations themselves allow this structure. When physicists take the mathematical description of a black hole and reverse the direction of time, the inward collapse becomes outward expansion. The event horizon remains, but its role changes. It is no longer a boundary you fall through. It is a boundary you emerge from. This is why white holes feel less like things and more like moments. A black hole has a history. It forms, grows, and evolves. It interacts with its surroundings. A white hole, by contrast, has no formation story that unfolds within time as we experience it. It does not gradually appear. It is simply there, already expelling matter, already defined by its horizon. From the outside, there would be no way to witness its beginning. The horizon marks a one-way edge of causality. You can observe what comes out, but you can never see what happens at or before that boundary. In this way, a white hole resembles a cosmic boundary condition rather than a physical object. The symmetry between black holes and white holes becomes clearer when we consider their event horizons more carefully. In a black hole, the event horizon marks the point beyond which escape is impossible. Signals sent outward from just inside never reach the outside universe. Time near the horizon slows dramatically for distant observers. In the extreme limit, it appears to freeze. For a white hole, the horizon also separates regions of spacetime, but in reverse. Nothing from the outside can cross inward. Signals aimed toward the horizon never arrive. From the outside, the horizon is always in the past of anything that emerges from it. The white hole is not something you approach. It is something that has already happened. This reversal challenges intuition because our experience of the universe is shaped by cause and effect. We expect events to have visible origins, but white holes present effects without accessible causes. Matter appears already moving outward. Energy flows without a source we can observe. In physics, this kind of behavior is deeply uncomfortable. Our universe strongly prefers processes that move from order to disorder. This preference is captured by the second law of thermodynamics, which states that entropy tends to increase. Black holes fit comfortably into this rule. They absorb matter, scramble information, and increase entropy. White holes do the opposite. They take what appears disordered and release it in a coordinated way. This is one reason white holes are considered unstable. In a perfectly isolated mathematical universe, they can exist. In a realistic universe filled with radiation, particles, and fluctuations, the delicate conditions required to maintain a white hole are easily disrupted. Even a single particle attempting to cross the horizon would break the symmetry, collapsing the structure into something else. But the idea persists because the mirror is exact in the mathematics. In the most complete solutions of general relativity, black holes and white holes appear together, connected through deeper spacetime structures. These solutions describe a universe where spacetime extends beyond what we normally consider boundaries. The interior of a black hole is not the end, but a bridge to another region. On the far side of that bridge lies a white hole. Whether such structures exist in reality is unknown. Most physicists suspect they do not persist in our universe, but their presence in the equations matters. It tells us that gravity does not fundamentally distinguish between inward and outward flow. The distinction comes from initial conditions, from entropy, from the direction time happens to take. This brings us to the idea of time reversal. If you were to record the formation of a black hole and play it backward, you would not see a star explode. You would see matter emerging from a horizon, assembling into a star, and then dispersing. Played backward, a black hole becomes a white hole. The laws of gravity allow this reversal. What they do not guarantee is that the universe will choose it. Our universe has an arrow of time. It points from past to future, from lower entropy to higher entropy. White holes point the other way. They are solutions that align with the equations of gravity, but oppose the statistical flow of time. This opposition makes them rare, perhaps non-existent, but it also makes them valuable as thought experiments. White holes act like mirrors held up to black holes, revealing which features are fundamental and which are contingent. For example, the fact that black holes trap light is not a mysterious one-off. It is simply one side of a symmetrical structure. The trapping occurs because space-time tilts inward. The release in white holes occurs because space-time tilts outward. The horizon itself is not inherently destructive or creative. It is a boundary defined by geometry. If you imagine drifting in space far from any extreme gravity, time feels steady. Distances behave as expected. But near a horizon, time and space trade roles. Directions that once felt optional become mandatory. In a black hole, the future lies inward. In a white hole, the past lies inward. This idea that time and space can swap roles is one of the most profound insights of general relativity. It reminds us that what feels absolute in everyday life is flexible at cosmic scales. From a distance, a white hole might look deceptively simple. Matter streams outward, cooling as it expands. Light escapes, redshifted by gravity. But the deeper truth is that you are not watching a process unfold. You are witnessing the aftermath of something you can never observe directly. In that sense, white holes are cosmic reflections. They do not tell us what happens. They tell us what must have happened without allowing us to see it. This mirror relationship also reframes how we think about destruction. Black holes are often described as devourers, endings, places where things are lost. White holes suggest that endings and beginnings may be connected more subtly. What appears lost in one frame may be released in another. What looks like a sink may have a source somewhere beyond our reach. None of this requires belief that white holes populate the universe. Their value lies in what they reveal about gravity, time, and symmetry. They show us that the universe's rules are broader than the behaviors we usually witness, that space-time is capable of more patterns than collapse alone. As we continue this slow exploration, another question naturally emerges. If white holes are the mirror image of black holes in theory, why does nature seem to favor one reflection so overwhelmingly over the other? Part 3. The event horizon that works backward. Black holes are wrapped in event horizons, surfaces where escape becomes impossible. White holes, if they exist, would also possess an event horizon, but one with reversed rules. Crossing it from the outside would be forbidden. Instead, the horizon would mark the moment when something emerges into space-time, unable to return to whatever state preceded it. This horizon would not hide the future, but the past. To understand why this reversal matters, it helps to pause and gently reframe what an event horizon truly is. Despite the dramatic name, an event horizon is not a physical surface. It has no texture, no temperature of its own, no sharp boundary you could touch. It is a geometric threshold, defined by the paths light can and cannot take. It marks the limit of communication. In a black hole, the event horizon is the line beyond which information cannot reach the outside universe. Signals sent inward pass a point where all possible futures lead deeper in. From the outside, that horizon appears to freeze time. Objects seem to slow, fade, and stretch as they approach it, never quite crossing, at least not within finite external time. For a white hole, the horizon performs the opposite role. It is not a line you approach, it is a line you have already passed, though not in a way that can be observed. The white hole's horizon marks the boundary of origin, the point at which matter, energy, or light enters our observable space-time. Everything beyond it lies forever in the past, inaccessible and unrecoverable. In this sense, the white hole horizon is not a veil over what will happen, but a curtain over what has already happened. This distinction is subtle but profound. Black hole horizons are about endings, white hole horizons are about beginnings, yet both are defined by the same principle: the limits of causality. Causality, the rule that causes precede effects, is not absolute in general relativity. Near extreme gravity, time and space become flexible. Directions that once seemed optional become enforced. Near a black hole, moving forward in time means moving inward. Near a white hole, moving backward in time becomes impossible. Imagine for a moment that you could hover far from a white hole horizon, watching matter stream outward. You would see particles, radiation, perhaps even complex structures emerging and dispersing. But no matter how powerful your instruments, you would never be able to trace those paths backward beyond the horizon. The information simply does not exist in your accessible past. This is what physicists mean when they say the horizon works backward. In black holes, information disappears from the future. In white holes, information disappears from the past. Both horizons enforce a one-way relationship, but in opposite temporal directions. This reversal becomes clearer when we think about light cones. In relativity, every event in spacetime has a light cone, a structure that defines which events can influence it and which it can influence. The future light cone contains all possible effects. The past light cone contains all possible causes. At a black hole horizon, the future light cone tilts inward. All futures lead into the hole. At a white hole horizon, the past light cone is truncated. The causes that would normally explain an event simply do not exist within spacetime. This makes white holes deeply uncomfortable for our intuition. We are accustomed to tracing events back to their origins. White holes deny that comfort. They assert that some events are simply given, not caused, at least not in any way we can access. From a purely mathematical perspective, this is allowed. General relativity does not require that every event have a cause within spacetime. It only requires consistency within the geometry. A white hole horizon satisfies that requirement. From a physical perspective, however, this creates tension. The universe we observe appears remarkably consistent in enforcing causal chains. Even quantum mechanics, for all its strangeness, preserves statistical causality. White holes sit at the edge of what those expectations can tolerate. This is why physicists often describe white holes as unstable. The horizon demands perfect isolation. Any attempt by external matter or radiation to interact with it would violate the required geometry. In realistic conditions, this would likely cause the horizon to collapse or transform. But even instability does not erase significance. The concept of a backward-working horizon helps physicists understand what an event horizon truly is. It reveals that horizons are not inherently destructive or creative. They are directional filters. They permit information to flow one way and forbid it the other. Which way is determined not by the horizon itself, but by the arrow of time. In our universe, the arrow of time points toward increasing entropy. Black hole horizons align with this direction. They swallow information into states of higher disorder. White hole horizons oppose it. They release information into more ordered configurations. This opposition may explain why we see one, but not the other. Yet there is another quiet insight hidden here. Horizons are not absolute in all frames of reference. What appears as a horizon to one observer may not appear as one to another. For example, an observer falling into a black hole experiences nothing special at the horizon locally. Spacetime feels smooth. The dramatic effects are global, not local. For white holes, the same would be true. There would be no wall of force, no glowing shell. The horizon's power lies in what cannot happen, not in what is felt. If you were somehow part of the matter emerging from a white hole, you would not experience a moment of crossing. There would be no sensation of beginning. You would simply exist, moving outward, your past truncated at the horizon. From your perspective, time would feel normal. The universe would expand ahead of you. This highlights another unsettling idea. From inside the allowed region of a white hole, the horizon is not a future boundary. It is a past boundary. It defines the earliest moment of your existence. There is no memory beyond it, not because memory failed, but because time itself does not extend there. In this way, a white hole horizon resembles the beginning of the universe as we know it. The Big Bang also marks a past boundary. We can trace everything back to it, but not beyond. Time itself appears to begin there. This resemblance has led some physicists to wonder whether the Big Bang could be understood as a kind of white hole horizon on a cosmic scale, not an object in space, but a boundary in time. Everything emerges, nothing precedes it in an observable way. Whether or not this interpretation is correct, it underscores the role horizons play in defining reality. They are not just features of black holes, they are fundamental to how space-time organizes information. White hole horizons, working backward, force us to confront the idea that the universe may include regions where explanation ends, not because of ignorance, but because of structure. As you rest with this idea, notice how quietly radical it is. It suggests that some events are not mysteries waiting to be solved, but boundaries that cannot be crossed. That the universe may contain beginnings that are not caused, only permitted. And as we continue this calm exploration, another question gently takes shape. If white hole horizons block access to the past so completely, what would it actually be like to witness something emerging from one moment by moment from the outside? Part 4. What happens if you try to approach one? Imagine drifting calmly through space, approaching what appears to be an empty region. There's no warning glow, no violent pull. But as you draw closer, the equations say something strange occurs. No matter how gently you try to approach, the geometry of space-time would prevent entry. Paths curve away. Time itself conspires to keep you outside. A white hole cannot be visited. It can only be observed from the aftermath it leaves behind. To understand why this happens, it helps to release the idea that motion through space is something you control. In general relativity, objects do not move because they decide to. They move because space-time gives them no other option. Every step you take, every orbit you follow, every beam of light you emit is simply tracing the shape of space-time itself. Near a white hole, that shape becomes quietly absolute. From far away, nothing seems unusual. Space looks calm. Distances behave normally. Your instruments detect no sudden forces, no extreme acceleration. Gravity does not pull you inward, as it would near a black hole. In fact, there may be no obvious sign at all that you are approaching something forbidden. But as you continue forward, space-time begins to do the work for you. The straightest paths, the geodesics, start to bend. Not dramatically, not violently, just enough that your forward motion no longer points where you think it does. If you adjust your course, space-time adjusts with you. Every allowed trajectory curves subtly outward. There is no direct road in. This is not resistance in the everyday sense. There is no push, no impact, no collision. Instead, the universe simply removes the option of approach. Like trying to walk north beyond the North Pole, every step forward becomes a step away, no matter how you orient yourself. Even light behaves this way. If you shine a beam toward a white hole horizon, it does not slow or scatter. It simply never arrives. The path that would carry it inward does not exist. Light follows space-time's rules perfectly, and near a white hole, those rules do not include entry. This is why physicists say that white holes are not protected by force, but by geometry. Time, too, plays a role in this quiet refusal. As you attempt to approach the horizon, clocks behave strangely, not in a dramatic freeze as with black holes, but in a subtler misalignment. The closer you try to get, the more the horizon remains fixed in your past. You are always too late. The event you are trying to reach has already happened, and nothing in space-time allows you to rewind to it. In this way, approaching a white hole is not like approaching a wall. It is like approaching yesterday. You can move through space, but not through time. The horizon marks a moment that cannot be revisited. You are separated not by distance, but by causality itself. This makes white holes fundamentally different from any object we are used to thinking about. A star can be approached, A planet can be orbited. Even a black hole can be crossed, at least in principle. A white hole offers no such interaction. It exists only as a boundary of emergence. From the outside, all you can do is watch what comes out. Matter emerges already moving away, already losing energy as it climbs out of the gravitational geometry behind it. Radiation spreads, redshifting as space-time stretches between you and its origin. Over time, whatever emerged disperses, blends into the surrounding universe, and leaves behind no trace of where it came from. There is no accumulation, no buildup, no lingering structure. This is another reason white holes are so difficult to imagine as persistent objects. Black holes grow, they gather mass, they shape their environment. White holes do the opposite. They shed whatever they have and then leave nothing behind that can be pointed to as the white hole itself. If you arrived late, if the emergence had already finished, you would find nothing, no scar, no remnant, just ordinary space, quietly expanding. In this sense, white holes are less like places and more like transitions. They are not destinations, they are moments. This perspective helps explain why white holes feel so elusive. They do not sit in the universe waiting to be discovered. If they exist at all, they would appear briefly, release something, and vanish without a trace. The only evidence would be the expelled matter itself, and even that would carry no clear signature of its origin. And yet, the equations insist on this behavior. They insist that there are configurations of space-time where approach is forbidden, not because of danger, but because of direction. The same mathematics that makes falling into a black hole inevitable makes approaching a white hole impossible. This symmetry is exact. If you imagine reversing every motion in a black hole encounter, every falling particle, every inward-pointing light ray, you do not get chaos. You get a white hole. You get a region that cannot be entered because entry would require moving backward through time. This highlights a deeper truth about horizons. They are not about force or matter. They are about information. They mark the limits of what can influence what. A black hole horizon blocks information from escaping into the future. A white hole horizon blocks information from being traced into the past. In both cases, the universe enforces a one-way rule. For you, as an approaching observer, this means there is nothing to do but remain outside. You cannot orbit closer and closer. You cannot skim the edge. You cannot send a probe across the boundary. Every attempt fails not through destruction, but through impossibility. And this impossibility is silent. There is no alarm, no catastrophic event, just a quiet absence of access. This has an interesting consequence for observation. If white holes exist, we would never see them directly. We would never see the horizon itself. We would only see what has already emerged, already moved away, already lost the context that gave it meaning. By the time light from the event reaches us, the white hole, if it can even be said to exist, would already be gone. This is why some physicists suggest that white holes may be effectively invisible, even if they occur. Their defining feature, the horizon, cannot be probed. Their only signature is aftermath, and aftermath is notoriously difficult to interpret. A burst of matter could come from many causes. A release of energy could be explained in many ways. Without access to the horizon, without the ability to approach or interact, a white hole leaves no fingerprint that says unmistakably, "This is what I am." As you rest with this idea, notice how it shifts your sense of exploration. We often imagine discovery as movement towards something, approaching, touching, measuring. White holes invert that expectation. They suggest that some features of the universe can only be known by what they leave behind, never by direct contact. They remind us that the universe is not obligated to be accessible. And so, as this quiet journey continues, another question naturally arises. If white holes cannot be approached or entered, what would it actually be like to witness one from a safe distance, watching matter emerge without ever knowing where it truly began? Part 5. Can matter really only come out? The defining feature of a white hole is one-way motion. Matter emerges, but nothing crosses inward. This sounds simple, but it violates our everyday experience of cause and effect. In all known physics, We see systems that allow both directions given enough energy. White holes break that symmetry. They behave like cosmic fountains, expelling mass without any visible source within our universe. To see why this is so unsettling, it helps to pause and reflect on how deeply symmetry is woven into physics. Most processes we observe can be reversed in principle. A ball can roll down a hill, and with enough energy, it can roll back up. Heat flows from hot to cold, but on the level of individual particles, the laws governing their motion do not forbid reversal. The asymmetry we experience arises from statistics, not from the fundamental equations themselves. White holes, however, introduce an asymmetry that is not statistical, but geometric. In a white hole spacetime, inward paths simply do not exist. No amount of force, no amount of energy, no clever trajectory can reverse the flow. This is not because something pushes matter away, but because spacetime itself offers no route inward. The direction of motion is built into the structure of the universe in that region. This is why physicists describe white holes as violating our intuition, but not the laws of gravity. The equations of general relativity allow spacetime to be shaped in ways that impose absolute directionality. Once that shape exists, motion follows inevitably. If you imagine releasing a particle near a white hole horizon, you do not see it hesitate or bounce. It simply moves outward, carried by the geometry beneath it. From the particle's perspective, nothing unusual is happening. It follows the straightest possible path available. It is only from the outside that the motion looks forbidden in one direction. This one-way behavior mirrors the behavior of black holes exactly, but in reverse. In a black hole, once something crosses the horizon, it can never come back out. In a white hole, once something has emerged, it can never go back in. The symmetry is perfect, but our universe seems to strongly prefer one half of it. One reason for this preference lies in entropy. Black holes are extraordinarily efficient at increasing entropy. They absorb matter, scramble information, and hide details behind horizons. White holes would do the opposite. They would release matter in a highly coordinated way, decreasing entropy locally. While this is not forbidden by the equations of gravity, it is extremely unlikely in a universe that began in a low entropy state and has been increasing ever since. This makes white holes appear not just rare, but unnatural within our cosmic environment. Yet the equations remain indifferent to this discomfort. They state clearly that if a region of spacetime exists with the right geometry, matter will only come out. The universe does not need to provide a mechanism for the emergence. The geometry is enough. This raises an important question. If matter can only come out, where does it come from? Within the framework of general relativity alone, the answer is unsettlingly simple. It comes from beyond the horizon, and beyond the horizon, spacetime as we know it does not extend. There is no inside in the ordinary sense. There is only a boundary where time ends. This is why white holes resist explanation. They are not machines that process matter. They are not engines converting fuel into output. They are boundaries in spacetime where the rules of causality are truncated. From the outside, the matter appears spontaneously. But spontaneity here does not mean randomness, it means absence of accessible cause. Some physicists have suggested that white holes might be connected to black holes through deeper structures. In these speculative models, matter falling into a black hole does not vanish. Instead, it passes through an extreme gravitational transition and re-emerges elsewhere as a white hole. In this view, white holes are not creating matter, but returning it. If such connections exist, the one-way motion remains intact locally. Matter falls in here. Matter comes out there. No signal passes between the two regions in a way that violates causality. The universe preserves information globally, even if it appears lost locally. Other models reject this connection and treat white holes as fundamental boundaries, cosmic outlets, where spacetime itself releases stored energy or information without any prior history within our universe. Both interpretations share a common feature. From the perspective of an external observer, the white hole does not allow inward motion under any circumstances. This absolute refusal is what distinguishes white holes from every other physical system we know. Even the most extreme environments, neutron stars, black holes, the early universe, allow interaction in both directions. White holes do not. This raises another subtle point. In quantum mechanics, absolute prohibitions are rare. Tunneling allows particles to cross barriers that seem forbidden. Fluctuations allow temporary violations of classical expectations. Yet in the classical description of white holes, no such loopholes exist. The geometry itself forbids inward motion completely. Whether quantum effects could soften this prohibition is an open question. Some researchers speculate that quantum gravity might allow small interactions across white hole horizons, destabilizing them almost instantly. This could explain why we do not observe stable white holes in nature. If white holes exist at all, they may exist only briefly, at scales where quantum effects dominate, appearing and disappearing before they can influence their surroundings in any lasting way. This possibility reframes the question. Instead of asking whether white holes are permanent objects, we might ask whether white hole-like behavior occurs momentarily, hidden within other processes. Perhaps during black hole evaporation. Perhaps during the earliest moments of the universe. Perhaps in regions where spacetime briefly rearranges itself before settling back into a more familiar form. In all of these cases, the defining feature remains the same. Matter comes out, nothing goes in. This feature challenges our instinct to seek balance. We expect give and take, input and output. White holes offer only output, and yet this asymmetry may be exactly what makes them useful as conceptual tools. They show us that not all asymmetries arise from force or preference. Some arise from structure. Once spacetime is shaped in a certain way, the outcome is fixed. As you rest with this idea, notice how it echoes themes from earlier parts of our journey. Time has a direction because spacetime allows it. Motion feels still because everything moves together. Horizons define reality not by what they are, but by what they forbid. White holes take this logic to its extreme. They are the universe saying no, not with violence, but with geometry. And as we continue this calm exploration, another question quietly waits ahead. If matter can only come out of a white hole, what determines how much comes out, how fast it emerges, and whether it happens all at once or slowly over time? Part 6. Where would the matter come from? This is where the mystery deepens. For a white hole to eject matter, that matter must originate somewhere. Some theories suggest it could be the time-reversed interior of a black hole, connected through a deeper structure of spacetime. In this view, what falls into a black hole might eventually re-emerge elsewhere, not destroyed, but delayed, released slowly or even explosively into another region of the universe. At first, this idea feels almost comforting. It offers balance. Nothing is truly lost. What disappears in one place returns in another. But as with many ideas in fundamental physics, the calm symmetry hides extraordinary complexity. To understand why this question is so difficult, we need to step carefully into the heart of a black hole, not physically, but conceptually. When matter falls past a black hole's event horizon, all of its future paths point inward. From the outside, it seems to vanish. From the inside, according to general relativity, it continues forward in time toward regions of extreme curvature. What happens next is where our understanding fades. At the center of a classical black hole lies a singularity, a point where density becomes infinite and the equations of physics break down. In these regions, general relativity can no longer tell us what happens. Quantum effects become important, but we do not yet have a complete theory that unifies gravity and quantum mechanics. White holes often appear precisely at this boundary of ignorance. In some extended solutions of spacetime, the singularity inside a black hole is not an endpoint, but a transition. Instead of matter being crushed into nothing, the equations suggest that spacetime might continue beyond the singularity into another region. In that region, the geometry flips. What was inward becomes outward. A black hole interior becomes a white hole interior. In these models, matter falling into a black hole is not annihilated. It is carried through an extreme transformation of spacetime and re-emerges somewhere else through a white hole horizon. The delay could be immense. From the outside, it might appear to take longer than the age of the universe. But from the matter's own perspective, time could pass differently. This idea is deeply speculative, but it arises naturally when physicists explore what happens if space-time is extended as far as the equations allow. One important feature of these models is that the black hole and white hole do not exist in the same region of space-time. They are separated by horizons and often by entire universes. Information does not pass freely between them. Causality remains intact. No signal can travel backward in time or violate known physical laws locally. From our point of view, a white hole connected to a black hole elsewhere would still look like matter emerging from nowhere. This preserves one of the most important principles in physics: conservation. Energy and information are not destroyed, they are relocated. This idea has gained attention in discussions of the black hole information problem, the question of whether information that falls into a black hole is lost forever. Many physicists believe that fundamental laws forbid true information loss. If that is correct, then black holes must have some way of returning what they absorb. White holes provide one possible answer. Another approach suggests that the matter ejected by a white hole does not come from a black hole at all, but from the structure of space-time itself. In this view, white holes are not recycling matter. They are releasing stored energy that exists as part of space-time's geometry. In general relativity, energy is not just something matter possesses. The curvature of space-time itself carries energy. In extreme conditions, that energy can manifest as particles. This is not hypothetical. It already happens in well-understood contexts, such as Hawking radiation, where black holes slowly emit particles due to quantum effects near the horizon. Some researchers have wondered whether white holes could represent a more dramatic version of this process, a region where space-time releases energy in a coordinated way, producing matter without any conventional source. If this were the case, the matter would not come from a previous object. It would come from the vacuum itself, shaped by gravity. This idea is unsettling because it blurs the line between something and nothing. But modern physics has already shown us that the vacuum is not empty. It is filled with fluctuations, fields, and latent energy. Under the right conditions, particles can appear and disappear spontaneously. White holes, in this interpretation, would be regions where those fluctuations are forced into permanence. Yet another perspective treats white holes as initial conditions rather than processes. Instead of asking where the matter comes from, this view asks a different question. Must everything have a cause within time? In classical physics, the answer feels obvious: yes. But general relativity complicates this intuition. Space-time itself can have boundaries where time begins or ends. The Big Bang is one such boundary. We do not ask what caused it in the usual sense, because before may not be a meaningful concept. White holes could be similar. In this view, a white hole is not ejecting matter that came from somewhere else. It is simply a boundary where matter exists because space-time allows it to exist there. The horizon marks the earliest moment of that matter's history. Asking what happened before is like asking what is north of the North Pole. This interpretation feels unsatisfying, but it is logically consistent. Physics does not require that every event have a cause in time. It only requires internal consistency. What all of these perspectives share is uncertainty. We do not know where the matter would come from because we do not yet know how space-time behaves under the most extreme conditions. White holes live at the edge of our theories, where answers dissolve into possibilities. And yet, this uncertainty is not a failure. It is a map. It tells us where our understanding ends and where future discoveries must begin. It tells us that gravity, time, and matter are more deeply intertwined than our current models can fully capture. If white holes exist, they may not be neat, symmetric counterparts to black holes. They may be brief, unstable, and rare. They may appear only at scales where quantum gravity dominates, leaving behind faint echoes rather than clear signatures. Or they may not exist at all in our universe, remaining mathematical ghosts, solutions that reveal the flexibility of spacetime without ever manifesting physically. Either way, the question of where the matter would come from forces us to confront something profound. It forces us to admit that our universe may include events whose origins lie beyond our accessible history. As you sit quietly with this idea, notice how gently it shifts your sense of certainty. Not everything needs to be traced back. Not every emergence needs a visible cause. Sometimes, physics allows beginnings that simply are. And as we continue this slow journey, another question waits just ahead. If white holes challenge our understanding of cause and origin so deeply, what do they reveal about time itself and the direction it chooses to flow? Part 7. White holes and the arrow of time. White holes are unsettling because they challenge the direction of time itself. In our universe, entropy increases, disorder grows, causes precede effects, but white holes appear to violate this arrow. They resemble objects that exist because of what will happen, not what has happened. In a sense, they are solutions where the universe runs backward locally, even if the rest of spacetime continues forward. To understand why this feels so deeply wrong, we need to slow down and examine what we mean by the arrow of time. Time, in the equations of physics, is surprisingly neutral. Most fundamental laws work just as well if time runs forward as if it runs backward. The equations of motion, electromagnetism, even gravity itself do not prefer a direction. They allow processes to unfold either way. And yet, our lived experience is unmistakable. Glass shatters but does not reassemble. Smoke spreads but does not gather itself back into a flame. Memories point toward the past, never the future. This asymmetry is not written into the laws of motion. It comes from entropy. Entropy is a measure of how many microscopic arrangements can produce the same macroscopic state. There are vastly more disordered arrangements than ordered ones. Because of this imbalance, systems almost always move from order to disorder. This statistical tendency gives time its arrow. It is not that the past is forbidden to return, but that it is overwhelmingly unlikely. Black holes align comfortably with this picture. They absorb matter, mix information, and hide detail behind horizons. From the outside, they increase entropy dramatically. Even the smooth surface of a black hole's event horizon carries entropy proportional to its area. Black holes are, in a sense, perfect entropy machines. White holes are the opposite. They take what appears to be a high entropy state and release it in a coordinated low entropy way. Matter emerges with direction, structure, and coherence. Information seems to flow outward, becoming accessible again. This reversal is not just rare. It appears to contradict the statistical direction the universe overwhelmingly follows. This is why white holes feel like violations of time, even though they do not violate the equations of gravity. In the mathematics of general relativity, time does not have a preferred direction. A white hole is simply the time-reversed version of a black hole. If you imagine every particle's motion reversed, every inward path turned outward, the equations remain valid. Gravity does not object. But the universe we inhabit is not just gravity. It is gravity embedded in a sea of particles, radiation, and interactions that collectively define a thermodynamic arrow. This creates a tension. White holes are allowed by the laws of spacetime, but discouraged by the laws of probability. They sit at the boundary between what is mathematically possible and what is physically plausible. To see this more clearly, imagine watching a video of a black hole forming. A star collapses. Matter rushes inward. An event horizon appears. Now imagine running that video backward. Matter streams outward. The horizon shrinks. The star reassembles. The backward movie is perfectly valid under the equations of motion. Nothing in gravity forbids it. What forbids it is statistics. The backward movie requires an extraordinary alignment of microscopic states. Every particle must move in just the right way. Any small disturbance ruins the reversal. In a universe filled with noise and fluctuation, such alignment is effectively impossible. White holes require that alignment. They require space-time and matter to be arranged with exquisite precision, resisting the overwhelming tendency toward disorder. This is why many physicists suspect that even if white holes can exist mathematically, they would be unstable in reality. The slightest interaction with the surrounding universe would break the conditions needed for their existence. And yet, the idea persists because it reveals something important. It reveals that the arrow of time is not fundamental. It is emergent. At the deepest level, time may not care which way it flows. The universe's preference for one direction arises from its initial conditions. Our universe began in a remarkably low entropy state. From that beginning, disorder has been increasing ever since. The arrow of time points away from that special beginning. White holes look like echoes of a different arrow. They resemble regions where the arrow points inward rather than outward, where order increases rather than decreases, where effects appear before causes, at least from an external perspective. This does not mean that white holes allow paradoxes or violations of causality. Within their allowed region, time still flows forward for anything that emerges. Clocks still tick normally. Causes still precede effects locally. The reversal appears only when we compare the white hole to the rest of the universe. In other words, white holes do not break time. They break our global expectation of time's direction. This subtlety matters. From the perspective of matter emerging from a white hole, there is no sense of running backward. There is no memory of a future cause. The horizon simply marks the earliest moment of existence. The arrow of time, locally, still points forward. It is only from the outside, looking in, that the behavior seems reversed. This mirrors another familiar situation in physics. Near a black hole horizon, time appears to slow down for distant observers. But, for the falling object, time proceeds normally. The contradiction is only apparent, not real. It arises from comparing different frames of reference. White holes may involve a similar mismatch, but in time rather than speed. From our frame, they look like violations. From their own frame, they may look entirely ordinary. This raises a profound possibility. What if the arrow of time is not universal? What if different regions of spacetime can have different temporal orientations, all consistent with local physics? White holes suggest that this is at least mathematically possible. Some cosmologists have explored this idea in speculative models of the early universe. In these models, time flows away from a low entropy boundary in both directions. From that boundary, one half of the universe experiences time flowing one way, and the other half experiences it flowing the opposite way. Each side sees the other as backward. In such a picture, white holes are not violations. They are neighbors with a different temporal orientation. While these ideas remain speculative, they highlight the conceptual role white holes play. They force us to ask whether time's arrow is a global rule or a local condition. They also connect white holes to one of the deepest mysteries in physics: why the universe began in such a low entropy state in the first place. The laws of physics allow far more disordered beginnings than the one we observe. Yet our universe started in an exceptionally ordered configuration. White holes look like remnants of that order. They resemble local pockets where the initial conditions of the universe briefly reassert themselves, producing order where disorder is expected. Whether or not such pockets exist, the comparison is instructive. It suggests that the arrow of time is fragile. It depends on history. It depends on boundary conditions, and it may not be the same everywhere. As you rest with this idea, notice how gently it shifts your perspective. Time may feel absolute as you breathe right now, steady and forward-moving. But at cosmic scales, time may be more like a direction chosen once, long ago, and followed ever since. Not an unbreakable rule, but a habit of the universe. White holes sit at the edge of that habit. They remind us that the universe could have been otherwise, that the flow we experience is not inevitable, and that the equations describing reality are more open-ended than our experience suggests. And as this quiet journey continues, another question slowly emerges. If white holes challenge the arrow of time so profoundly, could they be connected to the very beginning of time itself and to the birth of the universe we inhabit? Part 8. Could the Big Bang have been a white hole? Some cosmologists have noticed a quiet resemblance. The Big Bang looks mathematically like a white hole on the largest possible scale. Everything emerged, nothing entered, space itself expanded outward from an initial boundary. While this idea remains speculative, it suggests that white hole-like behavior may not be exotic at all, but woven into the very beginning of cosmic history. To approach this idea gently, we need to let go of a common image. The Big Bang was not an explosion that happened at a point in space. It was an expansion of space itself. Every region moved away from every other region. There was no center, no edge, no surrounding emptiness into which the universe expanded. Space, time, energy, and matter all came into being together. This already sounds familiar. A white hole, too, is not something that sits in space. It is a boundary of space-time. Matter emerges not from a location, but from a limit. There is no inside you could point to, only an outward flow that defines what comes after. When physicists describe the earliest moments of the universe, they often speak in similar terms. The equations of general relativity trace the expansion backward to a boundary where densities become infinite, and time, as we define it, stops. This boundary is not a moment in time preceded by another moment. It is the beginning of time itself. In that sense, the Big Bang behaves like a horizon. It is a past horizon. Everything we observe lies on one side of it. Nothing from before can influence us, because before may not exist in a meaningful way. The Big Bang hides the past in the same way a black hole hides the future, and a white hole hides its own origin. This parallel is not just poetic. It emerges from the mathematics. When cosmologists study space-time diagrams, they notice that the structure of the Big Bang resembles the structure of a white hole horizon. Both are one-way boundaries. Both allow emergence but forbid entry. Both define the earliest possible events in their respective regions. From our perspective, the universe has always been expanding outward from that boundary. We cannot approach it. We cannot observe it directly. We can only infer its existence from what has already emerged. This is exactly how a white hole behaves. Of course, there are important differences. A white hole, as traditionally defined, exists within an already established spacetime. The Big Bang, by contrast, defines spacetime itself. There is no external region. There is no outside. This makes any direct identification speculative. Still, the resemblance invites careful thought. If white holes represent regions where spacetime releases matter without allowing inward motion, then the Big Bang represents the ultimate release. All matter, all radiation, all structure emerges. Nothing enters. There is no surrounding universe feeding it. The universe begins by flowing outward. Some physicists have taken this resemblance seriously enough to explore models where the Big Bang is described explicitly as a white hole solution. In these models, the universe's expansion is not a unique event, but one instance of a more general behavior allowed by gravity. In one class of ideas, the Big Bang is connected to the interior of a black hole in another universe. Matter collapses in one region, passes through an extreme gravitational transition, and emerges as a new expanding universe elsewhere. From the inside, that emergence looks like a Big Bang. From the outside, it looks like a white hole. In this picture, universes give birth to universes. Each Big Bang is a kind of white hole event, connected to a black hole that formed elsewhere. Time does not loop back. Causality is preserved locally. But on the largest scales, space-time becomes a branching structure rather than a single linear history. This idea remains highly speculative. There is no direct evidence for such connections. But it has an appealing feature. It removes the need for a singular beginning from nothing. Instead, it replaces it with transformation. Another perspective takes a simpler approach. It suggests that the Big Bang resembles a white hole, not because it is one, but because both arise from the same underlying property of gravity, the existence of horizons and boundaries in spacetime. General relativity allows spacetime to have edges, not physical edges, but limits, where time or distance cease to be defined. The Big Bang is one such edge. A white hole horizon is another. They share a common language, even if they describe different situations. In this view, White holes are not exotic anomalies. They are small-scale echoes of the same principle that governs the birth of the universe. The universe itself began with a kind of one-way boundary, and white holes simply repeat that pattern on a smaller stage. This perspective also reframes how we think about beginnings. We often imagine that a beginning must have a cause, but physics does not require this. It requires consistency. If space-time has a boundary where time begins, asking what caused that boundary may be meaningless. It is not that there is no answer, it is that the question does not apply. The Big Bang challenges our intuition in this way. White holes do the same. Both suggest that the universe allows events whose origins lie outside the framework of cause and effect as we normally understand it. They are not violations of physics, they are expressions of its limits. There is another quiet similarity worth noticing. The early universe was extraordinarily ordered. Despite its high energy density, it had remarkably low entropy. Matter and radiation were distributed almost uniformly. Tiny fluctuations existed, but they were subtle. From this ordered beginning, all later complexity emerged. White holes also represent low entropy boundaries. They release matter in a coordinated way, not as random noise. They look like pockets of order appearing where disorder is expected. This connection has led some physicists to wonder whether the low entropy of the Big Bang and the hypothetical behavior of white holes are linked. Perhaps the universe's initial conditions reflect a deeper principle that allows order to emerge from boundaries in space-time. If that is true, then white holes are not oddities. They are reminders of the universe's origin. Still, caution is essential here. The Big Bang is supported by overwhelming observational evidence. Cosmic expansion, background radiation, primordial element abundances. White holes are not. Any connection between the two remains speculative. But speculation, when grounded in equations, has a long history of leading to insight. Black holes were once speculative. Gravitational waves were once speculative. Even the expansion of the universe was once speculative. Each began as a mathematical curiosity before becoming an observed reality. White holes may never follow that path, or they may appear in forms we do not yet recognize. What matters for now is what the comparison teaches us. It teaches us that beginnings and endings may not be as distinct as they feel, that the same gravitational rules govern collapse and emergence, that space-time can both hide and reveal depending on how it is shaped, and it gently suggests that the universe's birth may not have been a unique, inexplicable miracle, but an expression of the same deep structure that allows horizons, arrows of time, and one-way boundaries to exist at all. As you rest with this idea, notice how it softens the question of origin. The universe may not have burst into existence in isolation. It may have emerged the way everything else in physics emerges, through lawful structure, quiet symmetry, and the patient unfolding of geometry. And as this calm journey continues, another question waits just beyond the horizon. If white hole-like behavior may be written into the universe's beginning, why do we not see similar behavior unfolding around us today? And what prevents white holes from persisting in the modern cosmos? Part 9. Stability problems in a real universe. The equations allow white holes, but reality is less forgiving. Small disturbances, quantum fluctuations, stray particles, background radiation tend to destabilize white hole solutions. In simulations, even tiny interactions cause them to collapse or transform. This fragility may explain why we do not observe them. The universe is noisy, and white holes demand perfect isolation to survive. To understand this fragility, it helps to remember that Einstein's equations describe idealized spacetimes. They are exact, elegant, and internally consistent. But the universe we inhabit is not ideal. It is filled with particles, radiation, fields, and fluctuations at every scale. Even the emptiest regions of space are not truly empty. They are alive with background energy, drifting photons, and quantum uncertainty. White holes, unlike black holes, have no tolerance for this noise. A black hole is robust. It grows stronger as it absorbs matter and radiation. Every disturbance reinforces its defining feature, inward motion. A white hole, by contrast, depends on perfect outward-only behavior. Any attempt by matter or energy to cross inward, no matter how small, undermines the precise geometry required for its existence. This makes white holes exquisitely sensitive. In theoretical studies, physicists often test stability by introducing small perturbations. They add a tiny amount of matter, a slight fluctuation in energy, or a weak radiation field, and watch how the spacetime responds. For black holes, these perturbations usually settle down. The system absorbs them and returns to equilibrium. For white holes, the result is very different. Even infinitesimal disturbances tend to grow. The delicate balance that enforces one-way motion collapses. The spacetime geometry rearranges itself, often transforming the white hole into a black hole or eliminating the horizon entirely. The structure that forbade entry dissolves under the slightest pressure from the surrounding universe. This behavior suggests that white holes, if they ever form, would be fleeting. They could appear momentarily in extreme conditions, but they would not persist. The universe would not allow them to remain isolated long enough to become stable, long-lived objects. The background radiation alone, the faint glow left over from the Big Bang, would be enough to destabilize them. This contrasts sharply with black holes, which thrive in exactly the same environment. The reason lies in entropy again. Black holes align with the universe's tendency toward disorder. They act as sinks, collecting information and increasing entropy. White holes resist this tendency. They attempt to release order into a disordered environment. The universe pushes back. From a thermodynamic perspective, white holes are uphill processes. They require the universe to move against its statistical flow. Any interaction with the environment increases entropy and disrupts the low entropy configuration the white hole depends on. This makes the existence of white holes not just unlikely, but actively suppressed. There is also a quantum dimension to this instability. At very small scales, spacetime is not smooth. Quantum mechanics predicts constant fluctuations in energy and geometry. These fluctuations are tiny, but they never stop. Near a white hole horizon, such fluctuations would introduce inward-directed components that the classical geometry cannot tolerate. Some researchers argue that quantum effects would destroy a white hole almost instantly. The horizon would not have time to enforce its one-way rule before being overwhelmed by uncertainty. In this view, white holes are artifacts of classical gravity that do not survive contact with quantum reality. This idea gained support from studies of Hawking radiation. Black holes, due to quantum effects near their horizons, emit radiation and slowly lose mass. This process is subtle and slow, but it shows that horizons are not perfectly rigid. They interact with quantum fields. If black hole horizons are porous in this way, white hole horizons would be even more vulnerable. A white hole attempting to enforce absolute outward motion in a quantum universe would be fighting a losing battle. Another source of instability comes from the global structure of spacetime. White holes often appear in extended solutions that include multiple regions connected through horizons. These solutions are mathematically consistent, but they rely on precise boundary conditions. In the real universe, boundary conditions are set by messy contingent history, not by symmetry. Any mismatch between the ideal conditions required by the white hole solution and the actual state of the universe leads to collapse. This means that even if the laws of physics allow white holes, the universe may simply never arrange itself in the way required to support them. It is important to notice what this does not mean. It does not mean white holes are impossible. It means they are unstable. There is a difference. A pencil balanced perfectly on its tip is unstable. The laws of physics allow it, but the slightest disturbance causes it to fall. White holes may be similar, allowed in principle, unlikely in practice. This distinction matters because it preserves the conceptual value of white holes, even if they never appear as observable objects. They still reveal what spacetime permits. They still show us the full range of solutions hidden within gravity. They also help explain why the universe looks the way it does. If white holes were stable, the universe might look very different. We might see frequent eruptions of matter with no apparent cause. We might observe regions where entropy decreases spontaneously. The absence of such phenomena supports the idea that white holes, while allowed, are filtered out by the universe's noisy reality. There is another subtle aspect of stability worth mentioning. White holes are not just sensitive to external disturbances, they are sensitive to their own output. The matter emerging from a white hole carries energy and momentum. That energy interacts gravitationally with spacetime. In many models, this back reaction feeds back into the horizon itself, altering the geometry and undermining the conditions needed to maintain outward-only motion. In other words, white holes may be destabilized by the very act of releasing matter. This creates a paradoxical situation. The more a white hole behaves like a white hole, the less stable it becomes. Black holes, again, behave in the opposite way. The more matter they absorb, the more stable their horizons become. They deepen the inward tilt of spacetime. This asymmetry reinforces the idea that the universe naturally selects black holes over white holes. Yet, instability does not mean irrelevance. Many important physical phenomena are unstable. The early universe itself was unstable. Tiny fluctuations grew into galaxies. Certain particles exist only for fractions of a second, yet their effects shape the cosmos. White holes, even if fleeting, could still play a role in extreme environments or early cosmic history. Some researchers speculate that white hole-like behavior could occur during black hole evaporation, when quantum effects dominate and spacetime undergoes rapid change. Others suggest that white holes might appear at the smallest scales in quantum gravity processes that leave no lasting trace. In these scenarios, white holes would not be objects we could observe directly. They would be transient events hidden within more familiar phenomena. As you reflect on this fragility, notice how it reframes the mystery. The question is no longer simply, do white holes exist? It becomes, can the universe ever stay quiet enough to allow them? The answer, so far, seems to be no. The universe hums with motion, energy, and interaction. It does not sit still. White holes require stillness, perfect unnatural stillness, to persist. And yet, the fact that the equations allow them at all is telling. It suggests that spacetime's rules are broader than what the universe typically expresses, that beneath the noise, there is a deeper symmetry waiting quietly in the mathematics. As this calm exploration continues, another question gently presents itself. If stable white holes cannot survive in a noisy universe, could there still be brief moments, tiny flashes, where white hole-like behavior appears, leaving behind subtle traces we might one day learn to recognize? Part 10. Could white holes exist for an instant? Some physicists suspect white holes, if real, might be fleeting. They may form briefly at the smallest scales, perhaps during quantum gravitational events, and vanish almost immediately. These microscopic white holes would not shape galaxies or stars, but they could leave subtle signatures, bursts of energy, unexplained emissions, or anomalies in spacetime itself. To understand why this idea is taken seriously, we need to shift our sense of scale. When most people imagine white holes, they picture dramatic cosmic objects, comparable to black holes in size and power. But nature often hides its strangest behaviors in the smallest places. The universe, at its deepest levels, is not smooth or continuous. It flickers, it fluctuates, it seethes with temporary structures that exist for only the briefest moments. At quantum scales, even empty space is alive. According to quantum field theory, the vacuum is not nothing. It is a restless background of fields, constantly fluctuating in energy. Particles appear and disappear. Pairs form and annihilate. These events are normally tiny and fleeting, but gravity complicates this picture. When spacetime itself becomes part of the quantum game, entirely new behaviors become possible. This is where the idea of momentary white holes enters. Some approaches to quantum gravity suggest that spacetime, at the smallest scales, is not fixed. It can tunnel between different configurations. Just as particles can tunnel through barriers they cannot classically cross, spacetime itself may briefly adopt shapes that would be forbidden or unstable at larger scales. In this view, a white hole does not need to be a permanent structure. It only needs to exist long enough for spacetime to briefly reverse its flow in a tiny region. These hypothetical objects are often called microscopic white holes or Planck-scale white holes. Their size would be unimaginably small, far smaller than an atom. Their lifetime would be extraordinarily short, perhaps fractions of a second or less. But during that instant, something remarkable could happen. Energy could be released. In quantum gravity, energy and geometry are deeply linked. A sudden rearrangement of spacetime could force energy stored in curvature or fields to manifest as particles or radiation. To an outside observer, this would look like a sudden burst, an event without a visible cause. Such bursts would not be dramatic on human scales. They would not tear apart stars or warp galaxies. But they might be detectable with sufficiently sensitive instruments, especially if many such events occurred over cosmic time. Some researchers have wondered whether certain unexplained phenomena could be hints of this behavior. Short-lived gamma-ray bursts, fast radio bursts, high-energy cosmic rays with no clear origin. None of these have been convincingly linked to white holes, but the possibility remains open. What makes this idea appealing is that it bypasses the stability problem. A large white hole is unstable because it must remain isolated for long periods. A microscopic white hole does not face that challenge. It exists too briefly to be disrupted. It does not need to maintain perfect conditions. It only needs to flicker into existence and disappear. This is a familiar pattern in physics. Virtual particles exist only momentarily, yet their effects are measurable. Quantum fluctuations shape the behavior of fields and forces. Even black holes themselves, in some theories, may form and evaporate at tiny scales, leaving behind no direct trace. White holes, in this context, would not be exceptions. They would be part of the same restless fabric. There is also an intriguing connection to black hole evaporation. According to Stephen Hawking's work, black holes slowly lose mass by emitting radiation due to quantum effects near the event horizon. As a black hole shrinks, it eventually reaches a size where quantum gravity dominates. What happens next is unknown. Some models suggest that instead of vanishing entirely, a black hole could undergo a transition. Its interior could rebound, releasing stored information and energy in a final burst. From the outside, this could resemble a brief white hole event, a moment when the direction of space-time flow reverses before settling back into normality. In this picture, white holes are not separate objects. They are phases. They represent a transitional behavior of space-time when gravity and quantum mechanics interact at their most extreme. They appear not as stable entities, but as events, punctuations in the universe's ongoing evolution. This idea aligns with the broader theme we've been exploring. White holes may not be places you find, they may be moments you miss. If such events occur, they would be extraordinarily difficult to identify. Their signatures would be subtle, their causes would be hidden, and their explanations would compete with many more conventional possibilities. But difficulty does not equal impossibility. Physics has a long history of uncovering fleeting phenomena by accumulating careful evidence. Neutrinos were once thought undetectable. Gravitational waves were once dismissed as mathematical curiosities. Both required patience, precision, and new ways of listening to the universe. If white holes exist only for an instant, they may require similar ingenuity to uncover. There is another reason physicists take this idea seriously. It preserves symmetry without demanding stability. The equations of gravity allow time-reverse solutions. The universe, however, resists long-lived time reversal. Momentary reversals are a compromise. They allow the mathematics to be expressed without overturning the overall arrow of time. In this sense, fleeting white holes act like pressure valves. They release tension between symmetry and reality. They allow space-time to briefly explore configurations it cannot sustain. From a philosophical perspective, this is a satisfying outcome. It suggests that the universe honors its deepest laws without letting them dominate behavior at macroscopic scales. It keeps the strange confined to the small and the brief. As you rest with this idea, imagine the universe not as a static structure, but as a living process. At every moment, space-time is adjusting, fluctuating, negotiating between what is possible and what is probable. Most of the time, it settles into familiar patterns. Occasionally, it flickers into something rare. White holes, if they exist for an instant, would be part of that flicker. They would not announce themselves. They would not linger. They would leave behind only whispers, subtle deviations that hint at deeper structure. And perhaps that is fitting. The universe has always revealed its deepest truths indirectly, through patterns, not proclamations, through echoes, not declarations. White holes, in their fleeting form, would follow that same tradition. They would remind us that even the most one-sided processes may not be absolute. The time's arrow, while strong, may tremble briefly at the smallest scales. That space-time itself is capable of more nuance than our experience suggests. And as this quiet journey continues, another question begins to form. If white holes can exist even for an instant, what role might they play in preserving information? And could they be the missing link in understanding what truly happens to information that falls into a black hole? Part 11. Information, not destruction. One of the most important roles white holes play is philosophical. They offer a possible solution to the black hole information problem. If information falls into black holes but later emerges through white hole-like processes, then nothing is truly lost. The universe remembers everything, even if it takes incomprehensible time for that memory to resurface. To understand why this matters so deeply, we need to pause and consider what physicists mean by information. In everyday language, information feels abstract: facts, memories, messages. But in physics, information is precise. It describes the complete state of a system, the positions of particles, their energies, their relationships. If you know the information, you can, in principle, reconstruct the past and predict the future. The laws of physics at their most fundamental level are believed to preserve information. This principle is woven into quantum mechanics. Even when systems evolve in complex, chaotic ways, the underlying information is not destroyed. It may be scrambled beyond recognition, but it remains encoded somewhere in the universe. Black holes challenge this belief. When matter falls into a black hole, all the information about its internal structure appears to vanish from the outside universe. Only a few properties remain visible: mass, charge, and spin. Everything else seems erased. If the black hole eventually evaporates through Hawking radiation, what remains is thermal noise, radiation that appears to carry no information about what fell in. This apparent loss creates a deep conflict between general relativity and quantum mechanics. It is known as the black hole information problem, and it has troubled physicists for decades. White holes enter this story quietly but powerfully. If white holes exist, even briefly, they offer a way for information to return. In this view, black holes do not destroy information. They delay it. They store it in forms inaccessible to us, perhaps within their interiors or within the geometry of space-time itself. Over immense spans of time, that information could be released again, not backward in time, but forward, through white hole-like processes. This idea reframes black holes completely. Instead of cosmic erasers, they become cosmic archives. The information is not gone, it is hidden. One proposed picture imagines that as a black hole evaporates, its interior undergoes a slow transformation. Rather than collapsing into a final singularity, the interior geometry rebounds. The black hole transitions into a white hole, releasing the stored information in a final phase. From the outside, this release might be extraordinarily slow or incredibly sudden, depending on the details of quantum gravity. In some models, the delay between absorption and release could be longer than the current age of the universe. From our perspective, the information would seem permanently lost, but in principle, it would still exist, waiting. This preserves a comforting idea. The universe is fundamentally reversible at the deepest level, even if that reversibility is hidden behind horizons and timescales beyond imagination. Importantly, this does not mean information emerges in an obvious or readable form. It may come out highly scrambled, spread thinly across radiation and particles. Recovering it could be practically impossible. But impossibility in practice is not the same as impossibility in principle. Physics cares about the latter. White holes provide a conceptual mechanism by which information conservation could coexist with black hole horizons. They allow spacetime to obey quantum rules without demanding that information be accessible or useful to observers like us. This distinction matters. The universe does not promise clarity. It promises consistency. There's another subtle aspect to this idea. If information is preserved, then time itself may be more like a storage medium than a one-way conveyor. Events do not simply vanish into the past, they imprint themselves on the structure of spacetime, waiting to be re-expressed under the right conditions. White holes, in this sense, are not just physical curiosities, they are symbols of memory. They suggest that the universe does not forget. It may delay, it may obscure, but it does not erase. This idea resonates beyond black holes. It touches on a broader question. What does it mean for something to be truly gone? Stars burn out. Civilizations fade. Particles decay. And yet, the information describing those processes remains embedded in the correlations of particles in the radiation, filling space, in the geometry of spacetime itself. White holes extend this principle to the most extreme environments. They suggest that even when matter disappears beyond an event horizon, its story is not finished. Of course, this is not the only proposed solution to the information problem. Other ideas suggest that information escapes slowly through Hawking radiation itself, subtly encoded in correlations that are difficult to detect. Still others propose holographic principles, where information is stored on horizons rather than within volumes. White holes may not be necessary, but they are illuminating. They show that spacetime itself could act as a memory device, capable of storing and releasing information across vast scales of time. They show that destruction may be an illusion created by perspective. From outside a black hole, information seems lost. From a deeper view of spacetime, it may simply be displaced. This perspective invites a quieter, more reflective way of thinking about the universe. Perhaps nothing truly disappears. Perhaps events only move beyond our reach, beyond our light cones, beyond our patience. Perhaps the universe carries every moment forward, waiting for conditions where it can be expressed again. White holes, even as theoretical constructs, embody that patience. They do not rush. They do not announce themselves. They suggest that time itself may be more flexible than we imagine, capable of storing consequences until the universe is ready to receive them. There is a kind of comfort in this idea, not because it promises recovery or reversal, but because it suggests continuity. The universe is not a place of abrupt erasure, it is a place of transformation. Even endings may be temporary. As you sit with this thought, notice how gently it reframes loss. In physics, loss often means inaccessibility, not annihilation. White holes remind us that what is hidden may still exist, waiting beyond horizons we cannot cross. And as this quiet exploration continues, another question softly arises. If white holes help preserve information in principle, could we ever hope to detect that information returning? And if so, what would such a return look like to observers like us? Part 12. Seeing one without knowing it. If a white hole appeared somewhere in the cosmos, how would we know? From a distance, it might look like a sudden release of matter or radiation with no visible cause, a burst without a precursor, an explosion without a star. Astronomers have observed strange high-energy events that defy easy explanation, though none have been confirmed as white holes. For now, they remain whispers, not evidence. The difficulty begins with a simple truth. The universe is loud. Stars explode, neutron stars collide, black holes merge, magnetic fields snap and release energy in violent outbursts. Space is filled with processes capable of producing sudden, powerful signals. Against this backdrop, a white hole, especially a brief or a microscopic one, would not announce itself clearly. It would not come with a label. It would not repeat on schedule. It would blend in. If a white hole released matter or radiation, the signal would arrive at our telescopes stripped of context. We would see energy, motion, direction, but not origin. There would be no visible object to trace it back to, no surrounding debris field, no gradual buildup, just aftermath. And astrophysics, by its nature, is the study of aftermath. We almost never witness the beginnings of cosmic events. We see their echoes, light that has traveled millions or billions of years, arriving long after the moment that produced it. We reconstruct stories from fragments. We infer causes from patterns. A white hole challenges this method. Because its defining feature is the absence of a visible cause, it produces exactly the kind of signal that science is most cautious about interpreting. Extraordinary claims require extraordinary evidence, and nothing caused this is one of the hardest claims to support. Consider what astronomers actually measure. They detect photons, light across different wavelengths. They measure arrival times, energies, polarization. From these, they infer distances, environments, and possible sources. Every detection is filtered through models built from known physics. If a burst of gamma rays appears in the sky, astronomers first ask familiar questions. Could this be a supernova, a neutron star merger, a magnet or flare, an active galactic nucleus? Only after exhausting these explanations do they begin to consider something new. White holes sit beyond the edge of that list. Not because they are forbidden, but because they offer so little to work with. A white hole event would likely be brief. It would not repeat. It would not leave behind a persistent object. There would be no remnant to study later. By the time we notice something unusual, the white hole itself, if it ever existed, would already be gone. This makes identification extraordinarily difficult. There are, however, certain features that have caught physicists' attention. Some cosmic events appear to release enormous amounts of energy in very short periods of time, without obvious progenitors. Fast radio bursts, for example, are millisecond-long flashes of radio waves from distant galaxies. Most are now thought to come from highly magnetized neutron stars, but some exhibit properties that strain existing models. Gamma-ray bursts, the most energetic explosions known, also present mysteries. While many are well explained by collapsing stars or merging compact objects, a few defy simple classification. Their energies, durations, or environments do not fit neatly into established categories. None of these events are evidence for white holes, but they illustrate the challenge. The universe already produces rare extreme phenomena that push our understanding. White holes, if they exist, would have to be distinguished from these with care. What would make a white hole different? In principle, a white hole event would lack precursors. There would be no gradual brightening, no gravitational wave signal preceding the burst, no infalling matter heating up before release. The event would appear abruptly, fully formed. It might also exhibit unusual correlations. If the matter emerging carried information in a highly scrambled but non-random way, subtle patterns might exist in the radiation. These patterns would not encode a message, but they might deviate slightly from what thermal processes produce. Detecting such deviations would require extraordinary precision. Another possibility lies in timing. White hole events might occur without regard to their environment. Most astrophysical explosions occur in specific contexts, within galaxies, near massive stars, along dense regions of gas. A white hole might appear in a relatively empty region of space without surrounding structure to explain it. Even this, however, is not decisive. The universe is large, and rare events occur in unexpected places. The deeper problem is philosophical as much as observational. Science advances by connecting causes to effects. White holes, by design, sever that connection. They present effects without accessible causes. This does not mean they are unscientific, but it does mean they sit at the limits of what science can comfortably confirm. To claim a white hole detection, astronomers would need to rule out all plausible conventional explanations. They would need to show not just that an event is strange, but that it cannot reasonably be anything else. This is a high bar. So far, no observation has cleared it, but absence of evidence is not evidence of absence. White holes, if fleeting and rare, could easily escape notice. Or they could be misclassified, folded into other categories, their uniqueness smoothed over by statistical uncertainty. There is also the possibility that white hole signatures are subtle rather than dramatic. Instead of bright explosions, They might produce faint anomalies, slight deviations in energy distributions, small inconsistencies in space-time curvature, tiny mismatches between cause and effect that are too small to notice individually, but meaningful in aggregate. Detecting such signatures would require new kinds of observation, new ways of listening to the universe, instruments sensitive not just to energy, but to structure, to patterns that hint at unusual origins. This is not unprecedented. Gravitational waves were invisible to us until we built detectors sensitive enough to feel space-time itself, stretching and compressing. Neutrinos passed through Earth unnoticed for decades before detectors grew large and quiet enough to catch them. White holes, if they exist, may require a similar leap. They may not announce themselves with fireworks. They may whisper through statistics, through anomalies that only make sense when viewed together. And there's another quiet possibility. Perhaps we have already seen white hole-like events, but lack the conceptual framework to recognize them. Science does not just depend on better instruments, it depends on better questions. Before black holes were accepted, astronomers observed compact, invisible objects exerting enormous gravitational influence. They were there all along. The name came later. White holes may be waiting in the same way, not as confirmed objects, but as unexplained behaviors, waiting for a theory bold enough and careful enough to connect the dots. As you sit with this idea, notice how gently it reframes discovery. The universe may already be showing us everything it has. Our task is not to force meaning onto it, but to listen more carefully. White holes, if they exist, would not demand attention. They would slip past, unnoticed, folded into the background of cosmic noise. And perhaps that is fitting. The deepest structures of reality often reveal themselves not through spectacle, but through quiet inconsistency. Small reminders that our current stories are incomplete. As this calm journey continues, another question naturally follows. If white holes are so difficult to identify observationally, what role do they really play in physics, and why do theorists continue to take them seriously at all? Part 13. Inside the mathematics of spacetime. White holes remind us that spacetime is not intuitive. Einstein's equations do not favor human logic or experience. They allow bridges, loops, horizons, and reversals. White holes emerge not because physicists want them, but because the math permits them. They are reminders that reality may be far stranger and far calmer than our instincts suggest. When Einstein wrote the equations of general relativity, he was not trying to describe stars, planets, or even black holes as we imagine them today. He was describing a relationship. Matter and energy shape space-time. Space-time, in turn, shapes motion. The equations are compact, elegant, and deeply indifferent to everyday intuition. They do not care how things feel. They care only about consistency. When physicists explore these equations, they do not ask what seems reasonable. They ask what is allowed. And what is allowed is vast. The equations permit space-time to curve gently, as it does around Earth. They permit it to curve violently, as it does near black holes. They permit time to slow, distances to stretch, and paths to loop in ways that defy ordinary geometry. They permit horizons, surfaces that separate what can be known from what cannot. White holes arise from this freedom. They are not added by hand. They are not speculative patches or imaginative leaps. They appear when physicists solve the equations completely, without discarding solutions that feel uncomfortable. When the full structure of space-time is laid bare, white holes are already there, quietly embedded. This is one of the most important lessons white holes teach us. Physics is not obligated to match human expectation. In everyday life, cause comes before effect. Motion can be reversed with effort, boundaries can usually be crossed, but these are habits of a narrow environment: slow speeds, weak gravity, low energy. General relativity describes a universe far beyond those conditions. In that broader universe, time can behave differently. Mathematically, many solutions to Einstein's equations are time-symmetric. This means that if a particular space-time configuration is allowed moving forward in time, its reverse is also allowed. Collapse and expansion are equally valid. Inward and outward horizons are two sides of the same structure. White holes exist because the equations do not privilege one direction over the other. This symmetry often surprises people because it clashes with experience, but it is not unique to gravity. Classical mechanics, electromagnetism, and even many quantum equations share this time symmetry. The arrow of time emerges later from statistical behavior and boundary conditions, not from the fundamental rules. White holes sit precisely at this junction. They are solutions that honor the symmetry of the equations, but resist the statistical flow of the universe. The math allows them. The universe rarely expresses them. This distinction between what is mathematically allowed and what is physically realized is central to theoretical physics. The equations describe a landscape of possibilities. Reality selects a path through that landscape, guided by initial conditions, stability, and probability. White holes remind us how large that landscape really is. They also remind us that space-time is not a stage on which events unfold. It is an active participant. It can stretch, twist, connect distant regions, and impose directionality on motion. In some solutions, space-time forms bridges known as wormholes. In others, it loops back on itself. In still others, it creates boundaries where time ends or begins. These are not metaphors, they are features of the equations. White holes are one such feature. In mathematical terms, a white hole appears when space-time contains a horizon that separates a region with no past from the rest of the universe. That region does not evolve from earlier events, it exists as a boundary condition. The equations remain well-defined, nothing breaks, nothing explodes. The discomfort comes not from inconsistency, but from unfamiliarity. We are used to thinking of the universe as evolving step by step. White holes challenge that picture. They suggest that space-time can include regions defined not by evolution, but by structure. They suggest that some features of reality may simply be, without having formed in time as we understand it. This idea appears elsewhere in physics. The Big Bang, as we have discussed, is one example. It is not a moment preceded by another moment. It is a boundary. Asking what came before may not be meaningful. The equations describe what happens after, not what caused the beginning. White holes are similar, but localized. They are boundaries where space-time does not extend backward. The mathematics does not fail there. It simply stops asking questions about the past. This reveals something important about how physicists use mathematics. The equations are not stories. They do not explain why in a narrative sense. They describe how in a structural sense. When they permit something, it exists within the framework, whether or not it fits our intuition. White holes exist because space-time geometry permits horizons that work in both temporal directions. This is why theorists continue to take them seriously. Not because they expect to find white holes tomorrow, but because ignoring them would mean ignoring part of what the equations are telling us. And history has shown that doing so can be costly. Black holes themselves were once dismissed as mathematical oddities. Einstein was skeptical. Many physicists believed they would never form in reality. It took decades of theoretical and observational work to show that they are not only real, but common. White holes may follow a different path. They may remain mathematical features without physical counterparts. But understanding why they do or do not exist helps clarify the limits of our theories. They act as stress tests. If a proposed theory of quantum gravity eliminates white holes entirely, it tells us something about how time symmetry is broken. If a theory predicts brief white hole-like behavior, that tells us something about space-time at small scales. If a theory requires white holes for consistency, that is even more revealing. In this way, white holes serve as diagnostic tools. They expose assumptions. They reveal hidden constraints. They show us which features of our theories are fundamental and which are emergent. They also encourage humility. The universe has repeatedly shown that it is under no obligation to match our expectations. It does not care what feels reasonable. It follows its rules quietly and precisely. White holes remind us of this with unusual clarity. They are strange, but not chaotic. They are counterintuitive, but not violent. They are calm solutions to equations that describe the deepest structure of reality. And perhaps that calmness is the most important lesson. White holes are not monsters lurking in space-time. They are mirrors held up to our understanding. They show us that the universe is richer than our experience, broader than our habits, and more subtle than our instincts suggest. As this gentle exploration continues, one final question begins to take shape. If white holes are permitted by mathematics but resisted by nature, what does that tension tell us about the universe's preferences and about the quiet rules that decide which possibilities become real? Part 14. Why the universe may avoid them. Nature often permits possibilities it rarely uses. Just as negative energy states exist mathematically but remain elusive in practice, white holes may be allowed but suppressed. The universe seems to prefer processes that increase entropy, not reverse it. White holes resist that trend, standing quietly against the flow of cosmic time. To understand this preference, we need to listen closely to how the universe behaves when left to itself. Across every scale we can observe, from melting ice to expanding galaxies, the same pattern appears. Systems move from order to disorder. Differences smooth out, energy spreads, entropy rises. This is not a rule enforced by force, but a tendency written into statistics. There are simply more disordered arrangements than ordered ones, and so the universe drifts that way naturally. Black holes fit perfectly into this drift. They gather matter, they hide information, they increase entropy dramatically. In fact, black holes may be the most entropic objects in the universe. Their horizons store enormous amounts of entropy, far more than ordinary matter of the same mass. From the universe's point of view, black holes are efficient, cooperative participants in the grand unfolding of time. White holes are not. A white hole does not smooth differences. It sharpens them. It releases matter in a coordinated way. It takes something hidden and makes it accessible again. It creates order locally, even if disorder increases elsewhere. This is not forbidden, but it is disfavored. The universe does not prohibit white holes. It simply does not nurture them. This distinction is subtle but important. Physics is full of allowed states that are rarely realized, perfectly reversible processes, idealized symmetries, exact cancellations. They exist in equations, but real conditions almost never align precisely enough to sustain them. White holes appear to belong to this category. They require an extraordinary alignment of conditions. Spacetime must be shaped just right. No stray particles can cross the horizon. No background radiation can intrude. No fluctuations can disturb the geometry. In a universe filled with motion and interaction, this level of isolation is almost impossible to maintain. The universe is not hostile to white holes. It is simply indifferent. And indifference, over time, becomes suppression. Consider how rare it is to see entropy decrease spontaneously. It can happen in small systems, briefly. A few molecules can momentarily cluster. A fluctuation can create local order. But these events are tiny and fleeting. They disappear as quickly as they arise. White holes on any significant scale would represent a dramatic local decrease in entropy. They would stand out sharply against the universe's background behavior. And standing out is precisely what makes them unstable. The universe does not correct them with force. It overwhelms them with probability. Another way to see this preference is through time symmetry. The fundamental equations of physics allow processes to run backward, but the universe's initial conditions break that symmetry. Our universe began in an extraordinarily low entropy state. From that starting point, the arrow of time emerged, pointing toward increasing disorder. Everything we observe unfolds along that arrow. White holes point the other way. They resemble echoes of a universe that never was, a universe where entropy decreases, where effects precede causes, where order grows from disorder. Such a universe is not forbidden by physics, but it is statistically rare beyond comprehension. Given enough time and enough universes, it might exist. But our universe does not appear to be one of them. This helps explain why white holes feel so unnatural. They are not violations of law, they are violations of habit. The universe has habits. It forms stars from collapsing gas clouds. It forms galaxies from gravitational attraction. It forms black holes when mass becomes dense enough. These processes repeat because they are stable, probable, and reinforced by feedback. White holes lack that reinforcement. There is no natural process that feeds a white hole. Nothing falls in to sustain it. Nothing strengthens its defining feature. Every interaction weakens it. Every moment exposes it to disturbance. In this sense, white holes are lonely solutions. They do not fit into the ecosystem of cosmic evolution. Another reason the universe may avoid white holes lies in causality. Our universe appears to respect causal order very strictly. Even quantum mechanics, with all its strangeness, preserves causal structure at the macroscopic level. White holes flirt with the edges of causality. They present outcomes without accessible causes. They suggest that spacetime can produce events without a prior story. While this is mathematically allowed, the universe seems reluctant to express it physically. It prefers processes where cause and effect can be traced, even if the tracing becomes impractical. This preference is not philosophical. It is structural. The universe's geometry, initial conditions, and matter content all conspire to reinforce forward-moving causality. White holes, by contrast, require space-time to enforce backward-facing boundaries. That enforcement is fragile in a universe already committed to a direction. There is also a practical observational consequence. If white holes were common, the universe would look chaotic in a very different way. Matter would appear unpredictably. Energy would emerge without warning. Cosmic history would be filled with untraceable eruptions. Instead, what we see is a universe where even the most violent events have ancestry. Supernovae come from stars. Gamma-ray bursts come from collapsing systems. Black holes come from gravitational collapse. The universe tells stories. White holes do not tell stories. They interrupt them. This may be the simplest reason the universe avoids them. It is not designed, but it is consistent. It unfolds in a way that preserves narrative continuity. Events follow from prior events. Structures grow from earlier structures. Even randomness has context. White holes lack context. That does not make them wrong. It makes them out of place. Yet, there is something quietly beautiful about their exclusion. It suggests that the universe is not arbitrary. It explores its own possibility space selectively. It expresses some solutions and suppresses others, not by decree, but by consequence. The equations of space-time offer a vast menu. Reality chooses a limited diet. White holes remain on the menu, untouched, and perhaps that is enough. They show us that the universe could have been stranger, that time could have flowed differently, that beginnings and endings could have swapped roles. They remind us that what we observe is not the only way things could be, but it is the way they are. As you rest with this idea, notice how it softens the mystery. The absence of white holes is not a failure of imagination. It is a reflection of preference. The universe leans toward what is stable, probable, and reinforcing. It leans toward black holes, not white ones. But the fact that white holes are allowed at all tells us something profound. It tells us that beneath the universe's habits lies a deeper symmetry, a quiet openness to alternatives that were never chosen. And as this calm journey approaches its final stretch, one last question remains. If white holes are unlikely to exist as physical objects, what do they ultimately give us? And why do they matter, even if the universe never builds one at all? Part 15. What white holes teach us about reality. Whether or not white holes exist, they serve a purpose. They force us to question assumptions about beginnings, endings, and direction. They suggest that gravity may not only consume, but also release. And they remind us that the universe may have exits as well as entrances, even if those exits remain forever beyond our reach. At first glance, this may seem like a small role for such a strange idea. If white holes are unstable, unobserved, and possibly non-existent in nature, why spend so much time thinking about them at all? The answer lies not in what white holes are, but in what they reveal. White holes act like mirrors held up to our understanding of the universe. They reflect back the assumptions we make without realizing it. Assumptions about time, causality, permanence, and loss. By existing quietly in the mathematics, they ask whether those assumptions are truly fundamental or merely habits shaped by experience. One of the deepest lessons white holes offer concerns endings. In everyday life, endings feel absolute. A fire burns out, a sound fades, a life concludes. In physics, black holes seem to embody that finality on a cosmic scale. Matter falls in, light disappears, information appears erased. The story ends behind a horizon. White holes challenge that narrative. They suggest that what looks like an ending from one perspective may be a boundary from another. That collapse and emergence may be two faces of the same structure. That gravity, when fully understood, may not only gather and conceal, but also release and return. This does not mean the universe promises recovery. It does not mean what is lost will come back in a form we can recognize or use. It simply means that destruction may not be as fundamental as it appears. White holes invite us to think in terms of transformation rather than annihilation. They also reshape how we think about beginnings. We often imagine beginnings as explosive, dramatic events, moments when something suddenly appears out of nothing. But white holes suggest a quieter alternative. A beginning can be a boundary, not a burst, a limit where time itself starts, without requiring a cause within time. This perspective aligns naturally with modern cosmology. The Big Bang, as we understand it, is not an event that happened in time. It is an event that defines time. White holes echo this idea on smaller scales. They show us that space-time can include edges where asking what came before is not meaningful. This is not a failure of explanation, it is a recognition of structure. Another lesson white holes teach us concerns direction. We experience time as flowing inexorably forward. Causes precede effects. Entropy increases. This direction feels so fundamental that it is easy to assume it is written into the fabric of reality itself. White holes remind us that it may not be. The equations of physics are largely indifferent to direction. They allow time to run either way. The arrow we experience emerges from conditions, not laws. White holes exist because the laws permit them, even if the conditions of our universe suppress them. This distinction matters deeply. It suggests that the universe's behavior is not dictated solely by rules, but by context. That what we observe is one realization among many possible ones. That the deep structure of reality is broader, quieter, and more flexible than our experience suggests. White holes also teach us humility. They show us that not everything allowed by our best theories will appear in nature. And they show us that the absence of something does not make it meaningless. Many ideas in physics are valuable not because they describe objects we can point to, but because they clarify the boundaries of understanding. White holes define a boundary. They mark the edge between time-symmetric laws and time-asymmetric reality, between mathematical possibility and physical preference, between what space-time can do and what the universe tends to do. In doing so, they help physicists test theories. Any complete theory of gravity must account for white holes, either by explaining how they arise, how they are suppressed, or why the equations that allow them must be modified. They are a pressure point where ideas are forced to be precise. Beyond physics, white holes offer something quieter. They offer perspective. They remind us that the universe is not obligated to conform to intuition, and that intuition itself is a product of narrow conditions. They remind us that what feels permanent may be provisional, and what feels impossible may simply be improbable. There is also a subtle emotional lesson here. White holes suggest that the universe is not only a place of consumption and collapse, but also a place of release. Even if that release is hidden, delayed, or unreachable, its possibility exists within the deepest rules of reality. This does not promise hope in a sentimental sense. It offers something calmer, continuity. The universe does not tear pages out of its own book. It folds them, compresses them, hides them behind horizons, but it does not necessarily destroy them. Whether or not white holes ever appear as physical objects, they remind us that physics is not just a catalog of things, but a language of relationships, a way of understanding how reality can be shaped, constrained, and transformed. They remind us that gravity is not just a pull downward, but a geometry that can curve in unexpected ways. That time is not just a ticking clock, but a dimension that can tilt, stretch, and even end. And perhaps most importantly, they remind us that mystery is not a flaw. The universe does not owe us complete accessibility. Some regions are hidden, some questions dissolve when examined closely. Some possibilities exist only in equations, never in experience. White holes sit comfortably in that quiet space. They do not shout. They do not demand belief. They simply exist as an idea that broadens our view of what reality could be. As you lie here now, breathing slowly, consider this final image. Imagine the universe not as a machine grinding forward, but as a vast landscape of possibilities. Some valleys are deep and well-traveled, others are high and rarely visited. White holes belong to those high places, visible from afar, mapped by mathematics, but seldom reached by reality. They show us that the universe chose a path, but it did not erase the map. And in knowing that, there is a gentle kind of comfort, the sense that reality is richer than what we see, that the cosmos holds more possibilities than it ever expresses, and that even the strangest ideas, if they arise from careful thought and honest equations, have a place in our understanding. With that quiet perspective, we come to the end of this journey, not with answers sealed shut, but with questions softened and with a deeper respect for the calm, expansive logic of the universe itself.